Welcome to Colaberry AI Podcast, brought to you by Colaberry AI Research Labs. Today, enterprise teams have widespread access to large language models. A large language model, or LLM, is a type of AI that generates text and code based on probability. Yet, despite this access, the vast majority of enterprise AI integrations fail to scale effectively. These workflows start simple, but they often evolve into brittle, high-maintenance bottlenecks. They require constant human intervention just to keep running. This failure stems from a structural mismatch. Automation engineers are attempting to force probabilistic AI models into rigid, deterministic architectures. You see this in the reliance on trigger action platforms like Zapier, Pipedream, or N8N. These environments are built for a methodology of tool chaining, connecting one software to another through fixed sequences. Scaling AI operations requires a transition from these isolated tool chains to stateful, autonomous systems orchestration. If you are a veteran data engineer adopting early AI tools, the initial setup process is deceptive. When you first connect disparate software and trigger automated actions, the immediate feedback creates an illusion of progress. Building these discrete features feels productive. You see data move between applications without manual data entry. However, a structural flaw remains hidden. The entire system still relies on manual orchestration to function. As business logic changes, the human developer becomes the primary bottleneck, forced to constantly wire and rewire connections. By wiring AI into existing tools without changing the underlying logic, engineers create a faster, more complex version of manual labor. This diagram shows a directed acyclic graph, or DAG, a linear workflow that only moves forward. It relies on strict A to B to C API calls. Introduce a probabilistic LLM into this rigid framework, and you immediately create structural instability. This brittleness occurs because unpredictable outputs from the LLM inherently break rigid if-then triggers. The pipeline expects a square peg, the LLM hands it a slightly off-center rectangle, and the entire system crashes. We replace that linear sequence with a central orchestrator node. An agentic system utilizes this hub, surrounded by continuous feedback loops. Unlike a linear pipeline that pushes data forward until it breaks, this architecture is nonlinear and adaptable. An autonomous system does not crash when it encounters unexpected data. It dynamically routes the anomaly back to the orchestrator for reevaluation. Transitioning to this orchestrator model requires a change in your engineering objective. The imperative approach focuses on the mechanics. What specific tool should I use to connect node A to node B? The declarative approach asks, what final state does this system need to achieve? A declarative objective function means you program the system by describing the desired result, rather than dictating the specific steps to get there. By defining the objective, you shift the burden of routing and logic formulation off the human engineer and onto the AI model. In practice, this means a corporate training database transitions from a static display to an active, self-managing entity. When the system manages its own state, static dashboards lose their role as the primary driver of business decisions. Shifting from imperative logic to declarative objectives evolves your role. You stop operating as a pipeline builder and become an autonomous systems architect. To elevate a system from automated to autonomous, the architecture must possess specific technical capabilities. Let's look at the exact parameters used in the Colaberry AI system overhaul. This split-screen diagram illustrates the first critical capability, continuous state tracking. The system ingests real-time business activity smoothly into a central state engine without batch delays. This ingestion happens intrinsically, devoid of manual triggers or scheduled cron jobs. A cron job is a time-based scheduler used in operating systems to run tasks automatically at fixed intervals. The second capability is anomaly detection. The system identifies exactly where business logic is actively breaking. The third capability is prioritization. The AI ranks these anomalies based on severity. Contrast this continuous stateful monitoring against the legacy method, where a human manually reviews a weekly error log to figure out what went wrong days ago. The primary value of an autonomous system is its ability to maintain persistent context, flagging critical breakpoints before a human ever logs in. Tracking state is only half the equation. The system also needs to actively execute changes based on that tracked state. This diagram shows dynamic routing in action. Workflows are adjusted on the fly based on live performance data. The router deploys specific, granular AI agents to handle isolated tasks as needed. This architecture handles intelligent conversation routing and user follow-ups without relying on rigid, pre-programmed decision trees. The final step of the loop is crucial. The system continuously monitors the outcomes of those deployed agents to ensure the declarative objective was met. This entire cycle of intelligent routing, active agent deployment, and continuous monitoring happens perpetually in the background. True AI architecture is defined by dynamic execution and continuous autocorrection rather than the isolated automation of individual tasks. Achieving this architectural leap requires utilizing agentic coding environments like Claude Code. Claude Code is an AI tool that writes, edits, and executes scripts autonomously within your local development environment. Leveraging these environments encourages a declarative mindset, which reduces development cycles. This side-by-side comparison diagram provides a benchmark. Transitioning a standard integration build took 3 months. Rebuilding it as an autonomous system took exactly 2 days. This reduction in time does not happen because the AI types syntax faster than a human. The speed comes from the system's ability to handle dynamic routing internally, which eliminates the need to write thousands of lines of custom glue code. The rapid deployment we see today is a symptom of utilizing stateful architecture. Most enterprise professionals are currently asking the wrong question. What AI tool should I learn next? The question that matters for scaling enterprise AI is, what autonomous system am I trying to build? This requires stopping the development of isolated features and disconnected integration pieces. Instead, begin architecting comprehensive, intelligent systems that actually run the work, rather than just assisting the human worker. Thank you for listening in. Subscribe and follow Colaberry on social media, links in the description, and check out our website, www.colaberry.ai/podcast, for more insights like this. Designing autonomous enterprise architecture is the focus of the Colaberry AI Research Labs, helping organizations move from rigid tools to intelligent systems that scale.